Welcome back to Computer Lessons.
If you want to visit your friend's house, you need their physical address, like 123 Maple Street. But if you want to call them, you look up their name in your contacts list, because memorizing a random string of 10 digits for every person you know is impossible for the human brain. The internet faces this exact same problem every single second. Computers, as we learned in the last video, only understand numbers. They communicate using IP addresses like 142.250.185.78. But humans communicate using language. We want to type google.com or youtube.com. We need a translator, a massive global distributed database that instantly converts human names into machine coordinates. This system is called the Domain Name System, or DNS. It is often described as the phone book of the internet, but that analogy is too simple because a real phone book is a single static book. DNS is a dynamic, hierarchical tree structure that spans the entire planet and updates in real time. When you type a URL into your browser and hit enter, you trigger a complex chain reaction known as a DNS lookup. The first place your computer looks is not the internet, it looks at itself. Your operating system maintains a local cache of recently visited websites to save time. If the address isn't in the cache, the computer checks a special text file buried deep in your system folders called the hosts file. In the very early days of the internet, before DNS existed, this file was the only way to map names to numbers. Network administrators literally had to download a new text file every week to keep up with the growing web. Today, the host file is mostly empty, used only for testing or blocking specific websites by overriding the public DNS. If the answer isn't on your computer, your request leaves your house and travels to a recursive resolver. This is usually a server owned by your Internet Service Provider, ISP. Think of the recursive resolver as a librarian who knows exactly where to find information. It doesn't know the IP address of the website you want, but it knows who to ask. If it doesn't have the answer in its own memory, it starts a journey to the top of the hierarchy, the root zone. The root servers are the anchors of the internet, managed by an organization called IANA. There are technically only 13 root server IP addresses named A through M. However, these are not just 13 physical computers. They are hundreds of server clusters replicated all over the globe using Anycast routing. When the resolver asks the root server, "Where is google.com?" the root server says, "I don't know, but I know who controls the .com ending." It directs the resolver to the TLD nameservers. TLD stands for top-level domain, which includes generic extensions like .com, .org, and .net, or country codes like .uk or .jp. The resolver then rushes to the TLD server responsible for .com and asks, "Where is google.com?" The TLD server replies, "I don't have the IP, but I know which company manages that specific name." It provides the address of the Authoritative Nameserver. The Authoritative Nameserver is the final destination. This is usually hosted by the domain registrar like GoDaddy or a service like Cloudflare. This server actually holds the record. It answers, "Yes, google.com is at 142.250.185.78. The recursive resolver takes this final IP address and runs all the way back to your computer. But before it gives it to you, it saves a copy in its own memory for a specific amount of time. This is determined by the TTL, or time to live, a setting that tells servers how long to cache the information before checking again. This entire global journey, from your house to the ISP to the root, to the TLD to the authoritative server and back, happens in just a few milliseconds. It is a testament to the incredible speed of fiber optics and efficient software engineering. But DNS is not just for finding websites. It holds different types of data called records. The most common is the A record, which maps a host name to a standard 32-bit IPv4 address. As we transition to the modern internet, we are seeing more AAAA records, Quad A, which map names to the massive 128-bit IPv6. Addresses we discussed in the previous video. Then there is the CNAME record, or canonical name. This is an alias system. It allows you to say that www.google.com is actually the same thing as google.com, directing traffic without needing a separate IP address entry. For email, we use the MX record, or mail exchange. When you send an email, the mail server doesn't look for the website IP. It looks for the MX record to find the specific server handling email delivery. This allows a company to host its website on one server and its email on a completely different one. There are also TXT records, which hold arbitrary text data. These are used heavily for security verification. When you connect a domain to Google services, they ask you to add a specific code to your TXT records to prove you actually own the domain. However, the original DNS protocol from the 1980s has a major flaw. It was designed for trust, not security. By default, DNS queries are sent in plain text over UDP. This means anyone spying on the network, like a hacker on public Wi-Fi or a government firewall, can see exactly which websites you are visiting. This vulnerability allows for DNS spoofing, or cache poisoning. A hacker can trick a recursive resolver into saving a fake IP address. When you type bank.com, the poisoned cache sends you to a fake website that looks identical to your bank, stealing your login credentials. To combat this, we are seeing the rise of DNSSEC, which adds cryptographic signatures to records to prove they are authentic. But even with signatures, the privacy problem remains. Your ISP still sees every request you make because they own the resolver you use by default. This is why many privacy-conscious users manually change their DNS settings to use public resolvers like Cloudflare's 1.1.1.1 or Google's 8.8.8.8. These services often promise not to log your browsing history and are frequently faster than the default ISP servers. The latest evolution in privacy is DNS over HTTPS or DOH. This protocol encrypts your DNS request inside a standard HTTPS web packet. To an outside observer, it looks like you are just visiting a secure website. They cannot see that you are actually looking up a domain name. This prevents man-in-the-middle attacks and stops ISPs from selling your browsing data to advertisers. However, it also makes it harder for network administrators to filter malicious content or block distractingly bad websites on corporate networks. For network engineers, tools like DNS Lookup on Windows or Dig on Linux are essential. These command line tools allow you to manually query specific name servers, bypassing the cache to see exactly what is happening behind the scenes. They are vital for troubleshooting why a website might be down for some people, but working for others. The concept of propagation is another source of confusion. When you buy a new domain or change a server IP, it can take up to 48 hours for the change to be seen globally. This is because millions of resolvers around the world are still holding onto the old, cached data until the TTL expires. DNS is the glue that holds the internet together. It allows us to build a human-centric web on top of machine-centric infrastructure. Without it, we would be navigating a digital ocean, using only latitude and longitude coordinates lost in a sea of numbers. We have established the wires and the addresses, but most of you aren't plugging a cable into your phone. You are connecting through the air using invisible magic that passes through walls. In the next video, we will explore Wi-Fi physics. We will decode radio waves, frequencies, and explain why your microwave oven kills your internet connection.
Tell me in the comments, do you stick with your ISP's default DNS, or have you already switched to a custom one like 1.1.1.1 for better speed? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.